Welcome to Implementing a Data Infrastructure for Advanced Analytics. As Howard mentioned, I'm Eric Collier. I'm an Assistant Director of Automation and IT at CAI. Today, my goal is to provide an overview of the bricks and the mortar that make up a solid foundation for delivering advanced analytics. I will also walk through some typical analytics and demonstrate how they can be delivered on this foundation. Although it's not the focus of this talk, and I may only mention it briefly, data integrity is a key to delivering dependable analytics. This talk will get a bit techie at times. I hope you can bear with me. At the end of this presentation, as Howard mentioned, we can discuss any details, and I'm happy to answer any questions. And if we don't get to them all, feel free to contact me. When I was presented with the opportunity to speak at this conference, I quickly surveyed the available topics. And frankly, I couldn't believe my eyes when I saw the topic, implementing a data infrastructure for advanced analytics. I probably responded within a minute of receiving the request. For the past 10 years or so, manufacturing intelligence has been a leading passion of mine. Unfortunately, however, most of the projects that I'm involved in are startup and expansion projects, which have such a pace that more consideration is given to getting up and running than how it will need to operate effectively throughout its life cycle. I started thinking about the topic of this presentation, and my first question was, just what exactly are advanced analytics? Over the years, I've been asked to develop measurement systems for many business processes, process control systems, and information management systems. This is a list that immediately came to mind. You may initially think to yourself that some of these are not so advanced, and I would have to agree with you. Most of these are not advanced in an analytical sense. However, many of these require that we overcome significant challenges to produce them in a manufacturing environment. Although these may not appear that advanced, the data infrastructure platform that we will be discussing can make more advanced analytics accessible to include artificial intelligence and machine learning. I was introduced to the top line of this diagram a few years back when studying manufacturing intelligence. When I use the term manufacturing intelligence, I'm making a distinction between it and business intelligence. I think it's an important distinction. The data formats for manufacturing process data is quite different from the standard online transactional processing and online analytical processing models associated with most business intelligence solutions. Manufacturing intelligence is a process of successive transformations of data, transforming data into information, information into knowledge, and knowledge into wisdom. For manufacturing intelligence, the transformations performed on the data during this progressive process are contextualization, aggregation, integration, and visualization. As we transform the data, we achieve a better understanding of relationships, patterns, and principles. Some of you may not be familiar with it, but ISA S95 is a standard for integration. It is a template that I will use to define the relationships between systems used in our example manufacturing facility. I've heard it described as the flow of information from the shop floor to the top floor. This standard also makes a nice overlay for our discussion of advanced analytics. And like ISA S88, the batch process control standard, many suppliers and several large pharmaceutical companies have adopted ISA S95 as a platform. The hope is that with greater adoption, integration between systems will become increasingly easier. Instead of implementing an interface between SAP and Syncade, Emerson's MES product, we might be implementing a standard ERP interface. ISA S95 has levels. Level 0, we have the actual production process. At level 1, we have the sensors associated with the production process and the manipulation of the production process. At level 2, we have monitoring, supervisory control, and automated control of the production process. At level 3, we have workflow and recipe control, stepping of the process through states to produce the desired end products. Also at this level, we have the retention of records and optimization of the production processes. At level 4, the enterprise level, we have the establishment of the production schedule, material use, delivery, and shipping. Here we have a data infrastructure diagram that has ISA S95 levels as an overlay. This is a logical diagram abstracting the physical details. Some of the systems you see here could potentially reside at the enterprise, at another site, or in the cloud. However, regardless of their physical location, they still logically reside at the indicated level. Most assuredly, the components at level 1 and 2 will reside physically at the plant level. Potentially, though, any of the systems at levels 3 and 4 could be located at a remote facility or in the cloud. This diagram is not inclusive of all the systems that would reside at any of the levels, but focuses primarily on those systems that we'll discuss later in this presentation and those that will make up the primary components of our data infrastructure. At the enterprise level, level 4, you can see an enterprise resource planning system, ERP. This would perhaps be an SAP system, a JD Edwards system, or the likes. At level 3, we have a LIMS, a laboratory information management system, an MES, a manufacturing execution system, a data historian. We have an MDW-CDH, which is a manufacturing data warehouse or contextualized data historian. Also, you will notice that there is a DMZ box. DMZ stands for Demilitarized Zone. Within the DMZ, we have a remote desktop services, RDS server, and a report server. The DMZ is a protected network enclave, allowing certain communications traffic and denying other communications traffic. There may be many other systems at level 3, which is referred to as the manufacturing operations management level. A couple of other systems might include a computerized maintenance management system, or CMMS, a learning management system, LMS, or an electronic document management system, EDMS. These are common systems at level 3. On the left-hand side of the diagram, you will see the transformation of data into information and information to knowledge. On the right-hand side of this diagram, we see the groups possessing the domain knowledge. At the bottom, you see that the domain knowledge for the components at level 1 reside with instrument instrumentation, and electrical I&E group. Between layers 1 and 3, the domain knowledge primarily resides with operational technology, OT. OT is a newer term like DevOps, which has come into recent use. This term is relevant for our model. The OT group includes persons with networking knowledge, Windows Server and domain knowledge, and automation and controls engineering knowledge. With so many companies outsourcing or centralizing IT, systems residing at levels 3 on down are often neglected, even though they are critical to manufacturing operations. In this diagram, IT supports business machines and enterprise software solutions. You may notice that there is no Wi-Fi on this diagram. Any of these networks can be extended with Wi-Fi. However, putting the field level instrumentation on Wi-Fi can cause problems, and you have to be selective with the instruments you put on Wi-Fi. This is particularly true if you have critical instrumentation. This is a list of definitions I added for reference purposes. If you have automation experience, you'll notice that there is an asterisk beside OPC. OPC originally meant something else, but the OPC Foundation redefined it as Open Platform Communications. Although I mentioned that data integrity is not the focus of this presentation, good network architecture and network security is essential to data integrity and our data infrastructure. While discussing the data infrastructure diagram, I mentioned the DMZ. Without a DMZ, servers are often configured to span more than one network. This is called being dual homed. This is an incredibly risky practice from a security perspective, and it is very prevalent. Dual homing a server provides a bridge that can allow viruses and malware to jump across networks. Several pharma companies were hit hard by the NotPetya malware. It is estimated that this malware cost Merck $1.3 billion in losses. Aside from the business systems, this malware crippled Merck laboratory and process control systems as well. In our data infrastructure diagram, there is an RDS, Remote Desktop Services server, within the DMZ. This kind of server is often referred to as a jump server. It allows you to jump from one network to another in a secure way. An RDS server can support secure remote access. Automation vendors often need remote access to level 2 systems to support troubleshooting. The automation software can be installed on the RDS server, and the automation vendor can access it using a corporate VPN. Many supplier remote access solutions seriously compromise security. Active Directory integration is important. It allows the security controls of multiple computers to be managed as a single group. It also allows one common service, Windows Active Directory, to provide authentication for all the computerized systems at level 3 and below. When Windows Active Directory authentication is used, users only have to remember a single password, their Windows password. Active Directory integration also allows many applications to benefit from Windows security groups. These security groups can be configured to align with functional roles such as operator, supervisor, engineer, and administrator. Active Directory integration also allows for centralized management of numerous settings such as password complexity, history, and expiry. This reduces regulatory risk. We don't have to go to individual computers to manage settings. We know that all computers are configured properly per our group policy. In order for electronic records to be contemporaneous, time synchronization is critical. Otherwise, there could be more than one picture of the truth. Just a quick note about isolated networks. I've heard clients comment that they were safe because they had an isolated network and therefore didn't need virus protection. Virus protection is imperative because almost no network is truly isolated. A vendor may put their laptop on the network or put a thumb drive in a workstation, and more often than not, there are connections between networks for printing or internet access that people have not taken into consideration. Now, on to the key components of our data infrastructure. The first component, and probably one of the most essential components of our entire infrastructure, is our process data historian. Although some folks do, I can't imagine operating a manufacturing facility without a data historian. A data historian is invaluable and is the basis for almost every one of the analyses listed earlier: electronic production or batch reports, statistical process control, cycle time and downtime statistics, yield calculations, OEE, cross-batch comparison, and golden batch. The data historian collects the process data and stores it with a timestamp. It is a database of process data. In this diagram, what I'm trying to depict is the value of the agitator speed sensor on a tank during a mix phase. In this example, the PLC, programmable logic controller, is the process controller. The OPC server is providing access to the sensor's value, and the data historian is polling and retrieving the sensor value from the OPC server. I'll talk more about the OPC server in a few minutes. If the historian's polling rate is 15 seconds, every 15 seconds, the historian will retrieve the current process value from the OPC server and store it in its database. How useful is this? Since we are storing the vessel agitator speed consistently, we have objective evidence that during the mix phase of our manufacturing process, the agitator speed was maintained within the range determined in our process validation. And since it was captured automatically, it has more veracity than it would if it were recorded manually. Here are some aspects of the data historian which make it the perfect cornerstone for our data infrastructure. A data historian timestamps the data values that it collects. Historian data is often referred to as time series data. Typically, a data historian will only store tag value, time, and tag quality. Tag quality is a qualitative good, bad status for each tag value collected. I'm using the term tag. A tag is a reference to a data point you want to store. Tags can have engineering units, display precision, and other configuration parameters, but unlike the tag values themselves, which are stored each time the tag is polled, the tag definition is stored only once. In the example on this slide, we are looking at values and timestamps for tag TI557-001. This tag represents a temperature sensor. It looks like the equipment that this temperature sensor is tied to is slowly heating. Data historians poll their data sources. This polling rate is usually part of the tag configuration. Not all tags need to be collected at the same rate. Some tags may change very quickly and others not so quickly. It would not make sense to collect temperature values on a very large tank, say every second. Determining poll rates for tags should be a thoughtful process. Data historians apply data compression algorithms. At a time when 40 megabyte disk drives were rare and expensive, this was incredibly important. With the availability of and storage increasing and the cost decreasing, this is not as critical as it once was, but is still important, as we will see in the next slide. Data historians have security controls. This is great for data integrity. Users are not able to change values stored in the data historian, generally speaking. A user with administrative role may be able to change a value, but most historians will log this change in an audit trail. However, the only real justification for making such a change would have to do with something like a time synchronization issue. Most data historians come with a number of tools. What percentage of Excel functions does the average user use? Most companies that have data historians are only taking advantage of a fraction of its capabilities. Data historians come with tools to graphically trend data, provide reports on data, and some have direct data entry tools. Direct data entry allows you to capture those values which can't be captured automatically. You may have a few gauges or processes which aren't automated, and you want to store that data for analysis. Direct data entry allows you to do that in a controlled fashion, and in some systems will also provide a second-person verification step to ensure that the data was entered without error. Data historians have software programs which collect data from the data sources. These data collector programs can be installed on the same level, level 2, as the data sources. Should connectivity be lost to the data historian on level 3, the data collectors will store or buffer the data from the level 2 data sources, and when connectivity to the data historian on level 3 is restored, the data will be forwarded to the data historian and no data loss will have occurred. Some groups fail to take advantage of this feature by installing the data collectors on the same level as the data historian on level 3. Just to give us an idea of why data compression is implemented on most data historians, I've calculated the number of records collected from a medium-sized facility that is storing data for 10,000 tags. I worked at a medium facility one time that we historized roughly 14,000 tags. I believed our polling rates were 1, 5, and 15 seconds. 10,000 tags polled every 5 seconds would create 63,072 million records per year if some form of data compression were not used. An OPC server is a key component of our data infrastructure as well. In this diagram, an OPC server is shown as a centralized source of processed data. An OPC server is a computer that has a software program that interfaces with process control data sources and makes their data accessible to other systems. An OPC server can make processed data easily accessible from a number of sources such as the process control system, a distributed control system, a building management or building automation system, or directly from process controllers, PLCs themselves, on equipment skids. OPC is an open process communication standard. Before OPC, if you were developing a data historian or other system to interface with a vendor's control system, you would have to pay the vendor for the details of their communications protocol in order to interface with it. Although it is ugly, this diagram is meant to convey the value of OPC and an OPC server. In this diagram, you can see that the term OPC server refers not only to the computer that has OPC software installed on it, but also you can see that the term OPC server refers to a software program as well. It's a bit confusing since powerful multi-user computers are referred to as servers, as are some software programs. OPC uses a client-server architecture. In the OPC standard, an OPC server is a software program that publishes data per the standard, and an OPC client is a software program that consumes data from an OPC server. The OPC server, the client, will have the OPC server software installed on it. There are a number of vendors that make OPC servers. Some of these products have advanced features to include OPC server redundancy, such that the OPC server software can be installed on multiple computers so that if there is a problem with one of the computers, the other computer can continue to make the process data available to the historian and other process control systems. This feature eliminates the OPC server as a single point of failure in our data infrastructure. The components in green within the boundary of the OPC server are data collector components of the data historian. These components can be installed on the historian, but as I mentioned previously, it is better to be closer to the data sources to prevent data loss. Should the connection be lost between the OPC server and the data historian, the OPC client will continue to poll the OPC server per the tag configuration and buffer that data using store and forward. Depending on the size of the store and forward files, several days of data could be collected before any data would be lost. Once the historian is accessible, all the stored data will be forwarded to the historian. If we look at the lower section of the diagram, we see that the OPC server makes direct connections with the process controllers from various suppliers. The software programs that connect the OPC server to the process controllers are called drivers. The data historian doesn't have to worry about the details of these drivers with Allen Bradley, Siemens, Delta V, etc. The OPC server supplier manages this complexity for us. I found this quote and I think it's applicable. According to Wikipedia, Michael Ventura is an American novelist, screenwriter, film director, essayist, and cultural critic. I think his quote on context is quite fitting for our discussion. This brings us to the third key component of our data infrastructure, a contextualized data historian. In previous slides, we talked about how a data historian contains time series data and has only time as its context. We have the tag value, and we know that the tag value was collected at X point in time. Aside from a quality attribute, that's all we have. We don't know who the operator was, what the batch was, what the operation and phases were, what product was being made, or even if product was being made at the time that the tag value was collected. We may be collecting this information, but it's in another tag. The point of a contextualized data historian is to put data in context. If we are running a mixed phase on our processing equipment, we may be collecting the speed from the agitator speed sensor. We may be collecting the operator from the PCS, the process control system. We may be also collecting the batch context, what the batch is, what the product is, and we may be collecting the process context, the unit, the operation, and the phase. But each of these pieces of information are stored as individual tags in our data historian. Our contextualized data historian is where we bring all that information together. We can put our process values, the data that we collected from our equipment's instruments and sensors, into the correct batch and process context. The process of combining the process and batch context with the process values is called contextualization. This is our first key concept. Let's say that we have a clean out of place COP station where we clean portable tanks. We monitor the COP station supply line by polling the supply line temperature sensor every 30 seconds. We want to make sure that the temperature of the rinse water is not below 85 degrees C. In order to make this determination, we go to our data historian and inspect the data collected. But we need to put the time series data historian values into process context. In this case, we have to get the process context from the process control systems. We need to know the time when the rinse phase started and when the rinse phase ended. By identifying these markers, the start and end times for the phase, we now know which temperature sensor values are for our rinse phase. We have contextualized these supply line temperature values. From the process controller, we can see that the rinse phase started at 12:02:35 and ended at 12:09:05. The temperature values for the rinse phase are the values between and inclusive of the start and end times. Our second key concept is aggregation. By extending our previous example, we now look at, and now that we've contextualized the supply line water temperature values, we can aggregate them and perform calculations on them. We can calculate the minimum supply line water temperature, the maximum supply line water temperature, and the average supply line water temperature during our rinse phase. We can store these values, these aggregated values, in our contextualized data historian within the batch and process context. These can form the basis of an automated production report. We will skip our third key concept for a moment, integration. And we'll discuss, because we will discuss it in our upcoming analytical examples, which require data from multiple sources. We've already seen how an OPC server is a key component for integrated data from multiple sources into a single data historian. What we see here is a visualization example. This is an automated electronic batch report. This is a replica of an actual electronic batch report that was created using the type of infrastructure we've been talking about. All this data comes from the contextualized data historian. The report format is simple and does not require modification to report on any processing unit within the facility. Any contextualized batch data can be visualized in this format. Advanced analytics form a part of our overall measurement system. What exactly do we want to measure? If we have a document management system, we may want to measure how long it takes to review a document, how many review cycles a document has had, how long it takes to approve the average document. If we are constructing a maintenance and reliability system, we may want to capture how many times a valve has been cycled on and off, how many hours are on a pump, or the flow rates across an RO membrane before and after sanitization to determine the effectiveness of a sanitization cycle. The first step in building a measurement system is to define exactly what it is we want to measure. In our case, we want to measure average document review cycle time. For the second step, we need to first identify the components that make up the measure. For the average document review cycle time measurement, we will need the start and end times for each reviewer of a given document. For our average document review cycle, all the data will come from our workflow table in our electronic document management system. The third step, identifying the transformations, involves taking the data components we've obtained and transforming them into our measure. For the average document review cycle, we take the start and end times for each reviewer of a given document and calculate each review cycle for the document. Considering the cycle time of all reviewers, the document review cycle time is the cycle time of the longest review for that document. We do this for all documents to obtain the cycle time of each document and calculate the average. In some cases, these steps may be incremental. We may have to identify components and transform them to make progress on our overall measure. We'll see this in one of our more challenging examples. Two things we want to avoid: looking at a data store and saying, what can I make out of this data? Or concentration on the presentation of the measurement before we've developed it. This is an example of our first advanced analytic, cycle time. To calculate cycle time, we need to take into account total processing time, hold time, and fail time. Once we've calculated the cycle time, we want to store it in our contextualized historian. We can then compare cycle times for the process as a whole, or can focus on particular operations and phases to identify best case cycle times. We will want to examine this best case to identify the shift, the operator, the processing unit, and other factors that make this the best case. We'll want to investigate phases with hold times. We might determine that a particular shift is in need of additional training. We may identify that one process has a number of failures. Investigation might determine that there is an automation issue that needs to be resolved. You might find that one of the processing steps takes a long time and could be made more efficient. All these types of observations are possible once we start storing our cycle times. In this next example, we're going to take a look at OEE, overall equipment effectiveness. This calculation is significantly more complex than cycle time. OEE is a measurement of measurements. It considers an availability measurement, a performance measurement, and a quality measurement. Availability takes into account the operating time, which is the scheduled time minus any downtime. Operating time is the time the equipment was actually running and making product. Before we calculate the performance, we have to calculate the time to produce the units. The time to produce the units is calculated by multiplying the total number of units produced by the ideal cycle time. This is how long it would take to produce the total number of units if the equipment was operating at peak performance. We can then calculate performance by dividing the time to produce the units by the total operating time of the equipment. Quality is the number of units produced minus the number of defective units, with that difference being divided by the units produced. What we've done here is to follow our roadmap. We identified the measurement, identified the components and sources, and identified the transformations. To illustrate OEE, we'll take a look at a fictional cartoning machine. To make the math simpler for me, our fictional cartoner is a really slow cartoner. This machine produces 12 units per minute, or one unit every 5 seconds. This is our ideal cycle time, 5 seconds. Our cartoner is scheduled to run once per day for 8 hours on the evening shift. For our 8-hour shift, we had 17 minutes of downtime. Our operating time was therefore 463 minutes out of the total possible 480 minutes. This gives us an availability of our cartoner of 96.5%. If our cartoner was running at its ideal cycle time, it would have taken us 424 minutes to produce the 5,093 units. When we take this time to produce the units, the 424 minutes, and divide it by our actual operating time of 463 minutes, we get a performance measurement of 91.7 for our shift. When we take our number of good units, 5,093, minus the 21 rejects, 5072, and divide it by the total number of units, we get a quality measure of 99.6 for our shift. Thus, multiplying these all together, the OEE for our cartoner for our shift is 88.1%. With a data infrastructure like the one we've been discussing, we can easily display this value on dashboards all throughout the facility. We can also make our OEE cumulative for the month. We can then compare months. In doing so, we might notice that we have lower quality in the summer due to humidity causing more forming problems with our cartons. This is how we move from data to information to knowledge and to wisdom. Let's take a look at a third example, yield calculation. Calculating yield is a product-specific and in some cases, intellectual property exercise. So I can't go into details regarding any calculation itself. What I want to point out is that yield calculation requires the use of our third key concept, integration. When we are identifying our components and sources for this calculation, we find that we require data elements from more than one source. To create our yield calculation, we will need data from our laboratory information management system and our process control system. Here we have a fictional biotech process. During the fermentation and upstream processes, we take samples and send them to the lab for analysis. These lab analyses determine the concentration of the protein we are trying to produce. The results of these lab analyses are stored in our LIMS. In this case, our LIMS supports a standard database protocol, OLEDB. OLEDB is like OPC for databases. We don't have to understand the details of each specific database that supports the standard, but all modern databases, SQL Server, Oracle, MySQL, etc., support it. Our contextualized data historian pulls the LIMS database and pulls our test results and stores them in batch context. We are also capturing process values, batch context and process context from our process control system. Process values such as the amount of raw material added and the tank level at the end of the cycle are being pulled from the historian into our contextualized data historian in a batch context. Once all the components of the calculation have been obtained, the contextualized data historian can perform the yield calculation and store it in batch context. This is a case study that has as its basis a real-world example that occurred while I was working for a biotech facility a few years back. During a corporate audit, the auditor requested to see the differential pressure, the DP alarms, for our clean rooms. I'm no expert on clean rooms, but what I've taken from a few experiences is that pressure needs to be higher in a clean room than the surrounding rooms so that when an entryway or exitway is opened in the clean room, no bad stuff gets sucked in. Differential pressure involves measuring the pressure difference between the clean room and surrounding rooms. Our clean rooms had alarms when the DP dropped below a specified value. In our building automation system, the auditor saw a number of DP alarms and asked how we knew product had not been affected by these out-of-spec conditions. It was a good question. It took a thorough review of paper, batch records, and logbooks to demonstrate to the auditor that the rooms were not in use or were out of service being cleaned when the alarm conditions were active and the rooms were out of specification. Since we had a robust data infrastructure, a continuous data historian, OPC servers, and a contextualized data historian, I was able to propose that we contextualize all the DP measurements for the clean room and combine them in the production report for the processing equipment that was located in the room. In this diagram, the previous solution is taken one step further. Since we are now seeing a lot of non-viable particle counter systems in clean rooms and isolators, we can integrate this data into our process equipment production report as well. In this example, we are getting the batch and process context from the processing equipment's control system. We are getting the differential pressures, DPs, from the environmental monitoring system, and we get the non-viable particle counts from the particle monitoring system. We can then contextualize and aggregate the processing values for the processing equipment and store them in batch context in the contextualized data historian. We can do the same with the differential pressures and the particle counts. When the processing equipment is not in use, we can capture those alarms and store them in an out of use context in the contextualized data historian. We can easily produce a single report for the processing equipment in the room and include both the DP and particle count values, as seen on this example. Most data historians provide tools for statistical process control. These two tools include run charts and control charts. As a process is running, current process values can be displayed in run charts or control charts. These run charts and control charts provide graphical confirmation that a process is operating according to historical norms or within statistical control limits. This is an example of a run chart. One thing to be aware of is that although the chart gives the impression of continuous data, we know that the data is being pulled and stored periodically. The historian and its tools use interpolation to smooth out the graphs between actual values that the historian has stored. This is an example of an X-bar chart. An X-bar chart is a type of statistical control chart. It differs from a run chart in that it has statistical control limits, upper and lower limits, which are statistically calculations. These upper and lower limits act as visual references for determining if the process is operating within limits. This brings us to our case study on SPC. This case study is based on a real-world solution provided a few years ago. There was a filling machine that had a check-weigh system. However, the check-weigh system could only determine empty syringes and perhaps grossly underweight syringes, but was not accurate enough at operating rates to determine if the filling target weights were being met. We were significantly overfilling to reduce the likelihood that we would not meet the label claim. This was costly. You can imagine that losses involved in overfilling a 500 milligram syringe by 10 milligrams each to ensure no underweight syringes were produced. For every 50 syringes, you lose an entire syringe. When a lot produced 450,000 syringes, you have in essence a loss of 9,000 syringes per batch. The problem provided another challenge. The filling machine did not have a mechanism for finely tuning the syringe volume or for making automatic adjustments as the filling line pressure fluctuated as the volume in the filling feed tank decreased. The filling machine had a knob which you could turn one click clockwise to increase the fill weight or one click counterclockwise to decrease the fill weight. During the filling operation at regular intervals, the operators would take a number of syringes, a sample set of 16, and use a mechanical device to extrude them onto a balance, which would capture the expelled volume and store those values in limbs. If the volumes appeared to be moving from the last sample set, the operator would make an adjustment to the filler by turning what I refer to as the roulette knob. This process not only resulted in significantly overfilled syringes in the range of 510 to 515 milligrams or so on average, the operator would often make an adjustment based upon an outlier in the data, an underfill causing a deviation and manual weighing process for the entire lot. 450,000 syringes weighed manually. My goal was to provide a rules-based control strategy for controlling the filling machine that used statistical process control. For our historian, the SPC tool only supported data that was in the historian. The first thing I had to do was get the expelled weight values out of limbs in near real time. In this case, I had to use database triggers within the limbs to write the weight values to the contextualized data historian when new entries were created in the limbs for this specific expelled weight test. I don't think I would have to do that today, since most of the contextualized data historians that are available now can monitor remote databases and determine when new entries are made and pull that data into the contextualized data historian. In any case, I was able to get the expelled weight values into the contextualized data historian in near real time. Now the operator could look at a control chart and determine if the average weight of the sample set was trending towards the upper control limit or down towards the lower control limit. With the SPC chart, we could make a rules-based control strategy. For example, if the weight was trending upward for 2 sample sets by 2 sigma, the operator would turn the control knob one click counterclockwise. That concludes our case studies on our examples of advanced analytics. There are many more examples that we could discuss. We could talk about countless energy monitoring and maintenance and reliability examples that are possible on the kind of data infrastructure that we've been discussing. There are a couple of topics I want to cover that I hope will convince everyone of the importance of building a solid data infrastructure. I want to talk a few minutes about source system reporting. Source system reporting is very common. When delivering large projects, it is often perceived as the right thing to do to ensure that the project schedule is met. We'll have the vendor do it. It's their equipment and they know what they're doing, and it's the best thing for our timeline. This is usually only a half truth. Frequently, vendors are no more adept at developing reports for their equipment than are our own automation teams. I recently worked on a data integrity remediation project for an oral solid dose facility. This facility had milling machines, tablet presses, and tablet coders provided by several different vendors. Many of these systems did not meet current data integrity standards and had to be upgraded. I was amazed at the quotes these vendors provided for producing production summary reports. Some of the quotes were in excess of $30,000 for a single report. And with source reporting, it's not just the initial cost, it's the maintenance and support costs. Granted, process reporting for this kind of equipment is not complex, but what if you need to make a simple change to a report? You have to call the vendor and they have to quote it, the change, and then the change has to be made, and then verification and validation has to be performed. So when we use the vendor's reporting solution, we are dependent upon that vendor to make the changes. And when we have numerous vendors, we have a plethora of reporting solutions. Perhaps the greatest downside is that with most of these vendor solutions, we don't have access to their process data. We can't integrate the data with other data, and we don't have access to data to perform process analysis. Worst case is that the vendor reporting solution produces a paper-based PDF report, which gives us no usable data. Although source system reporting may provide a perceived schedule benefit, it has some serious downsides. Here's a summary of downsides to source system reporting. There are a plethora of technologies to support. Most likely the data is pigeonholed and not accessible for analyses. Ongoing dependence upon the supplier for change. And often there are compliance issues with the supplier's reporting solution. What's another option? With the data infrastructure that we've been talking about, centralized reporting is the way to go. The process control on the processing equipment has the process values, the process context, and often the batch context. With our OPC server, regardless of the process controller used by the vendor, we can connect to it and we can expose the process values and store them in our data historian. With a little bit of work, we can contextualize, aggregate, and aggregate it, and store the max force, min force, average force, etc., and report on it. In the process, we have stored all the raw process data, and we have stored aggregates in the contextualized data historian, which can be used by other tools for analyses and support process optimization. Data federation. I want to discuss one more technology called data federation. Data federation can be used in place of aggregation and integration. With federation, the software connects to numerous data sources within the facility. Once the data sources are exposed, reports and analyses can be configured, which will access data from the multiple sources to produce the reports. At first glance, this appears like a great idea and a fantastic shortcut. However, there are some serious downsides to this type of solution. First, each time a report is requested, the data is accessed from the sources and the values calculated. If the report requires any significant volume of data, the report can take a while to be produced and can also have a negative performance impact on the source system. A second issue is that since the systems doesn't store contextualized aggregated values, the source systems have to stay in place. If we get a new LIMS, for example, we have to leave the old LIMS in place versus retiring it when we get the new LIMS if we want to continue to have access to our historical reports. Similarly, since the system doesn't store contextualized aggregated values, these values aren't accessible to other tools for analysis and visualization. Finally, if a process is changed, such as a rinse is added or removed, historical reports for the processing unit will either not work or include faulty data. Here's a quick summary of the downside of federation. By the way, most of the tools that use federation are not going to say that they use federation and are going to stress some of the aspects such as ease of integration or their presentation. Real quickly, because this is a very complex topic that honestly I don't understand incredibly well. Machine learning. From Wikipedia, machine learning is the study of computer algorithms that improve automatically through experience. It is seen as a subset of artificial intelligence. Machine learning algorithms build a mathematical model based on sample data known as training data in order to make predictions or decisions without being explicitly programmed to do so. Machine learning algorithms are used in a wide variety of applications, such as email filtering and computer vision, where it is difficult or infeasible to develop conventional algorithms to perform the needed tasks. Until recently, the primary use of machine learning in our industry has been in vision systems for fault detection, where machine learning solutions are being used in place of human vial inspection, such as in a vial or syringe inspection. Images of out of specification, cloudy vials, cracked lyo cakes, impurities, etc., are used to train the system. These systems are quickly replacing humans for inspections. Machine learning is also breaking into our industry in another way and is supporting process control strategies that will optimize the manufacturing process in a way that standard control strategies cannot. In this diagram, we have a ML solution deployed at level 2, which is directly managing the process. The ML algorithm is receiving process values from the OPC server, evaluating those values against the model, and then modifying the process set points directly. Such a solution will not only optimize cycle time and yield, it will also prevent any number of deviations and be responsive in a way that no human could. Here are a few keys to success for a flexible data infrastructure. Don't judge the book by the cover. Presentation is the least complex phase of any analysis. Be wary of proprietary solutions with proprietary interfaces. These tend to pigeonhole your data. This also includes application-specific solutions, such as an OEE appliance to bolt onto processing equipment. If you stay away from source system reporting, there are countless automation integrators that can look at the processing equipment tags and size up the context tags and the instrument tags in a few hours. Use a context data historian or a manufacturing data warehouse. These flat databases are easy to build and index to support queries on billions of records in sub-second time spans. Well, that's it for today. I hope that this has been helpful in some way and that you've learned something about data infrastructure for advanced analytics.